looking at bounded search tree algorithmic technique to design FPT algorithms. So, one thumb rule for problems for which you can apply this is if you can manage to find some small number of elements out of which something is forced into every solution, then you try and branch on one by one on that subset, right. So, in the case of vertex cover, we know that one of the endpoints must be in every solution. So, you have a subset of size 2 where at least one is forced into any solution that gave us a two-way branching. In the case of feedback vertex set, we had it to work harder. We needed to do some pre-processing, make sure the graph is minimum degree 3. Then we argued that out of the top 3k high degree vertices, one of them must be in every solution of size at most k. That gave us a branching rule. Then, so typically problems where we want to apply bounded search trees, you want to find some small subset among which you can force some of them, one of them or some small subset of them that in any solution, then that gives you a branching technique, and you can bound the depth of the branch because the solution size drops at every step. Then so we saw examples, vertex cover, feedback vertex set. What else did we see? That's all. So for example, let's quickly see this de-hitting set problem before I get to. I'm going to do a couple of more examples, but today's examples are a little non-trivial. But let's just do some simple. What is a de-hitting set problem? You have a universe. Let's say it's 1, 2 up to n, and you have a family. Where each Fi is some subset of U and cardinality of Fi is D. And the question is, does there exist U prime subset of U, cardinality of U prime is less than or equal to K, such that U prime intersects right. So, you have D element subsets of my universe. So, that is what. So, one example would be U with some. My family is 1, 3, 4, 2, 4, 5, 1, 4, 5, 1, 2, 5, and so on. Right. So I have 3 element subsets of that universe, and I want a small sized subset of my universe that intersects with each of these sets in the family. Right. So it hits every set. So that's why it's called a hitting set problem. And I'm asking, is there a k-sized solution, right? Typically, you are interested in minimum sized hitting set. So the decision version would be, is there a k-sized hitting set, and k is the parameter for us, right? So what would be a branching algorithm for us? That's it, right? Go to any Fi, say F1, then you know that in my solution 1 has to be there, or 3 has to be there, or 4 has to be there. Maybe both of them, or all 3 of them, but at least 1 has to be there, or 3 has to be there, or 4 has to be there. That's it. That gives you a branching. So that's a 3-way branching. And now suppose I pick 1 into the solution, then you remove all sets that contain 1. Right? In the remaining family, now you are looking for a k minus 1 sized hitting set. In the other branch, you pick 3 and do the same. In the other branch, you pick 4. So what would be the running time? d to the power k. It's a d-way branching to the depth k d to the k, right. So, in fact, this is what we did for vertex cover, because vertex cover is a two heating set, right. Every edge would be a set, and we said either this or that has to be there, but of course, that's just sort of a starting point. So, if you have a d heating set, immediately this gives you a branching strategy, which gives you a d to the k times some poly n, right. A naive algorithm would be n choose k, try all possible subsets of size k and check whether it hits, but this gives you d power k. So, this is a prototypical branching, a problem which is useful for branching. You can model many of these branching things as like a deheating set. Basically, you identify, you're working with some graph, you want to hit, you want to pick some subset where you say at least one of this must be in my solution. So, that gives you a branching step to a depth of k and you get this. Okay. So, that is how you do bounded search tree based algorithms, but this is slightly different. I mean, you need a little bit more work, and let's see how we will do this, right. So, what is the problem I am interested in? You are given a k different strings, each string is like this or some alphabet, small sized alphabet, and I have a demand of d and I want some sort of a center string, a string which is not far from each of the strings in the Hamming distance. So, Hamming distance is the number of positions where this string and that string differ. That is the Hamming distance. I want the Hamming distance to be at most d. So, is there such a string for this? Oh, this one itself will work. ACBA, its distance to x1 is 0, its distance to x2 is 1 and 2, and distance to x3 is these two. Okay, good. Okay, so that's a question, right? So, my parameter is d. Okay, so this suggests, okay. So, let's I mean, in this example x1 worked, it was not intentional, it just worked, but I am going to use this for my FPT algorithm. Okay, so try y equal to x1. I am looking for a string of length L. Let us try x1, right. When will this not work as a solution? If there is some xi whose distance is more than d, right. Okay. So, if distance between y and xi then we are done, else let xj be such that is strictly greater than or equal to d plus 1. Then let us try to learn something from this, right. So, what have we found out? So, I tried some candidate string, let us call it y, and somehow with some xj I have d plus 1 or more mismatches, right. Then what can we learn about the solution we are after? Right, I want to get some branching and some learning which will help us into branching. Okay. XG also want to work, sure. But I want some refinement of y, and then I want to move forward, make some progress, right. So, right. So, let us look at these positions. I claim that in the final solution we are after, at least in one of these positions, the actual value must be equal to this character. That is the learning. In the solution I am after, let us look at the positions where y and xj differ, and there is some character sitting here. So, in the final solution, this must be equal to this, or this must be equal to this, or this must be equal to this. If not, you will have this same problem of at least d plus 1 Hamming distance with xj, right. So, what I am going to do now is somehow fix try branching. So, I am going to solve this d plus 1 many sub problems where I will fix this character to be equal to the character of xj in that position, and I want my solution I am after to be one distance less from this. So, this is sort of my progress string. Okay. So, let me write down what I am saying. So, let's okay, we will create a more general problem, okay, a generalized problem. The generalized problem is this: input is I have x1, x2, xk plus some other string, a candidate. Okay. I mean, the problem is that I might change this to this, and in some other branch I do not want this to be changed again. Then you are getting into various loops. I want to carefully capture what I am doing. So, this is one, and I have a measure, let us say some L which is less than or equal to D. The question is, does there exist a y star such that distance from y star to xi is less than or equal to D for all I up to k, and in addition distance from y star to y is less than or equal to L. Okay. So, slightly generalized problem from here. So, which is that apart from the k strings, I am also given another string, and I want the solution I am after to be of distance at most d from each of this, but with respect to y, I want it to be at most L. This L is what I am going to use to capture my progress. It is going to come down one by one slowly. Okay. So, how do I map this problem to that? I mean, if I really want to solve this problem, then what sort of instantiation I have to do here to get this problem? Choose y to be x1, choose L to be D, right? Then it is not saying anything new, it is the same problem. Except now as I go into the recursive step, I have this y and this L will keep changing. Okay. So, now I start with y equal to x1, I try this, if not I manage to find this. Now, I will solve d plus 1 sub problems of this type. What are these d plus 1 sub problems? Else solve d plus 1 sub problems where you pick where L becomes L minus 1 whatever was before, and my y is y with 1 of d plus 1 positions replaced by the corresponding character of xj. So, what I am saying is I will take this, replace it by this character, and I get a y, go here, solve that problem. Now, L I am going to change it to L minus 1. So, that means the solution I am after should be of difference L minus 1 from this new string. So, that means okay. And so on. So, in the other sub problem I am going to replace this by the corresponding character and look for L minus 1 and continue this. And what would be the end condition or tail condition when L is 0, what happens? So, if L is 0 would be the end condition, what happens when L is 0? Or how do you solve this problem when L is 0? That is it exactly right. So, when L is 0, what am I asking? I am saying find me a string whose Hamming distance from y is 0 and it has to be of distance at most d from each of this. That means y, it must be only y. So, then it is same as asking is y the solution, if so answer is yes, if not answer is no, right. So, if y is 0 answer yes, sorry y is the solution. So, so the way you are thinking is that I start with this string, I have a d plus 1 branching. So, I arbitrarily pick some d plus 1 positions where these guys differ and I say okay, I know in my solution I have to fix this guy to be that particular character, you know, and here there will be some other positions where this is fixed. So, there is d plus 1. Now, I want somebody which is a distance at most L minus 1 from this and continue. So, this height would be at most L, but L is at most L is d to start with. So, what you get is something like a d plus 1 times d times everything else, right. But this is the length of the string. Actually, I called it L. So, somehow we need a branching, we need some fixing of positions, characters in some positions, and just starting with one of the exercise gives me that handle. And you can argue correctness of this algorithm. because we know that if there is a solution, then in that position that solution has to be one of these, and then it will be like remaining thing would be d minus 1 away from that particular string, and so on and so forth. Okay, so here's an example where how do you branch is not immediately obvious, but once you start with some solution or look at slightly general problem, it gives you a handle to branch. Okay, let's get back to the vertex cover problem again. There the measure will be slightly different, and we will look at the branching algorithm for that again, which I alluded to the last time. And that is this vertex cover above right. So what is the problem? You are given an undirected graph I said perfect matching, but this works even for maximum matching, and you are given a matching M. And parameter is K, and if you ask the question, does there exist a vertex cover of size okay, if this is a problem, we know how to solve it. Even if I did not give you the maximum matching, just want to find is there a vertex cover of size at most K, we have very good FPT algorithms whose running time, what we saw was something like 1.46 power K, but I also told you that there are better algorithms with running time of this type. But now I am going to tell you my parameter is not K, but K minus size of the maximum matching given to me, because clearly this is a K has to be greater than or equal to size of the matching. So this number is greater than or equal to 0, right? Because given any matching any matching size is a lower bound for the size of the vertex cover. So for any vertex cover, matching size is a lower bound. So now I am giving you, okay, can you do K minus maximum matching as a lower bound? So that means if I am after a C power K algorithm, the parameter I am interested in is something like this. Right? And I argued briefly last time why this is a more interesting parameter than just K. Because one trivial way to solve this, even if I had not known these great FPT algorithms, is that if K is less than size of the maximum matching, I will say no, there is no such vertex cover. Otherwise, in particular, I said if you have a perfect matching, then the number of vertices is at most 2 times K. Then you can even use your brute force algorithm and choose K 2 power n algorithm. Any of this would give you an FPT algorithm. But that's not a great FPT algorithm because we are using it when K is large. Okay. So this kind of parameterization falls into this class of parameterizations called above guarantee parameterization. Right, which means that there is some guarantee known, and I want my parameter which exponential blow up I am allowing you is not on the entire solution size, but on this difference, solution minus the guarantee node. Okay. So, you see that getting at this kind of an algorithm can be more challenging now, right, because what is allowed is something much smaller than k. Okay. So, what we will actually solve, we will come back to this problem later. We will solve the following problem, because we are going to use LP techniques. So, what is LP opt? Given vertex cover, you know how to write a linear program, an integer linear program for that, right. We have seen this. So, an integer linear programming formulation for minimum vertex cover is minimize summation xi. There is a variable for every vertex, and it's 1 means it's into the solution, 0 means it's not. That's sort of an interpretation. And for every edge uv, xu plus xv is greater than or equal to 1, and xi is, so it's actually a 0-1 linear programming for vertex cover. This exactly captures vertex cover, right. Now, if I relax this to linear program, then you can solve this LP in polynomial time. You get the optimum solution for the LP. So, again an observation we saw last time is that LP opt is less than or equal to size of the minimum vertex cover, right. Why is this? Because you are relaxing. So, minimum vertex cover will also satisfy your LP, and you might get actually even smaller, because the minimization objective function, you might get a minimum value, smaller value by relaxing from integrality constraints to fractional values, right. So, now I can ask the following question: k minus not LP opt of G. By that I mean, you write the vertex cover LP relaxation for the graph, solve it, and you get the optimum value. That value is smaller than, so your minimum vertex cover, integral vertex cover is greater than or equal to this. So, that difference is at positive. So, now I ask, because otherwise if k is smaller than LP opt, then you know that there is no such vertex cover, because minimum vertex cover size is strictly more than the LP opt. So, k must be greater than or equal to LP opt. So, I will ask this question. Okay, so, now you are given the k minus the LP opt, that quantity as the parameter, and we want to design an FPT algorithm for this. Okay, we are going to design a branching algorithm. Okay. In fact, we won't even design a new algorithm. We are going to analyze some simple old algorithm, and we will argue that in the branching algorithm. So, what? Okay, important thing about branching algorithms is that we said, oh, you identify some small subset where at least one is forced, that gives you a branching thing, and in every branch your measure drops, whatever the function of k, right, it drops. That is what helps you to bound the height of the tree. Okay. So, we will argue that this measure now is not k, that this difference drops in both the branches. Okay. So, I mean, we are just solving the vertex cover problem. Is there a vertex cover of size at most k? So, we will go to the graph and say, okay, I will pick this vertex or its neighbors into the solution. Okay. But when I do that branching, it is not about k dropping. K dropping is easy. We saw that as long as you pick a non-isolated vertex and say either I pick into the solution, that vertex into the solution, all its neighbors into the solution, in your recursive subproblem k drops. But here now I want to choose my vertex in a way that not just k drops, k minus LP opt drops, because if k drops by 1 and the LP opt of the new problem also drops by 1, then the drop cancel out. Okay. So, I want to make sure that that does not happen, then I am in business. So, that is what makes it challenging to capture, to measure how this parameter drops in each branch. Okay. So, the starting point would be, remember, recall we had this Nemoser-Trotter theorem, which said there exists an optimum solution to vertex cover LP in which each variable gets value from 0, half or 1. Right. Even though this constraint allows you for any fraction, we actually showed a way how to solve this LP using basically bipartite matching. Took 2 copies of the graph, added some corresponding edges. He said solve this bipartite vertex cover problem, and from there we can solve the original LP vertex cover, and that actually said that your values are not just arbitrary fractions. If not 0 or 1, it is only 0, half or 1. This is one part of the Nemoser-Trotter theorem. The other part, if you remember, what was the other part of the Nemoser-Trotter theorem? Is that once I solve the LP and I get my 0, half, 1 solutions, without loss of generality, you can collect into your vertex cover all vertices which get 1 and throw away all those which get 0 for the integral vertex cover problem. For my optimum vertex cover problem, so it said that there exists an optimum vertex cover, right. So, this is the integral that contains all vertices V such that XV star, the optimum. Okay, so let us call this X star, and no vertex V such that so now we prove this. Do you remember how we did? By showing that what you get is a crown, right. So, essentially you suppose you solve the LP and you get 1, 0 and half. These are all the vertices where the LP puts the value 1. These are all the vertices where the LP puts the value 0, and these are all the values LP puts half. What we argued is that this partition forms a crown, so we can include all of this into my solution, throw away all of this and work on this remaining graph, and this actually gave us a 2k sized kernel for vertex cover, right. In that process we showed this. So, this also gives you a pre-processing rule that whenever I have solve the LP, my ultimate goal is to answer this question. Okay. So, I will solve my LP, and if LP says, oh, LP opt is greater than k, then I immediately say no, there is no such vertex cover. Otherwise, I am going to pick all of this into my solution, throw away all these vertices from the graph because this is an independent set, these edges are covered. Work with this remaining graph where every vertex has LP as put value half. Okay. Now, one more thing we can show is the following. See, what would be nice is if on this graph also, when I solve the LP, it manages, suppose it manages to put some vertices 0, some vertices half, some vertices 1. Then I can further reduce this graph, right, by getting rid of the zeros and ones. So, I will just see if that's possible. I mean, this is also LP gave this and LP gave all of these guys half, but it may not be the only optimum solution. All halves may not be the only optimum solution. There may be another optimum solution where some are zeros and some are ones and some are halves. If I manage to get more zeros and ones, that gives me an opportunity to reduce the graph even further. Okay. So, I will keep on trying this, and when does this whole thing stop? If all half is the unique optimum solution. Now, can I actually detect this? Can I always find this is a question, right? So, that takes us to this next theorem. So, I already used some notation vertex cover LP, right? If for all x in B, okay, let me write down what is that I am interested in. I just want to know, I mean, I want to get to a solution where all halves is the unique optimum solution. And after that, I am going to do some very simple branching and argue that this measure drops in each branch. That's the goal. Okay. So, first, can I get to all halves as a unique optimum solution? So, half is the unique vertex cover LP of G if and only if the following happens: for all x in B, the opt of okay, is the statement clear? So, this is about the vertex cover LP. Is the statement clear? So, what I am saying is this is the unique optimum solution for the vertex cover LP if and only if remove a vertex, look at the new graph, write the new LP, write the LP for that graph, solve it, look at the optimum, and optimum will be smaller because you are looking at a smaller graph. But it does not go down very much, that is what it says. It will be smaller, but it is at least the original opt minus half. If this happens for every vertex, then all halves is a unique optimum solution. Okay. So, I will prove this, and then assuming this theorem, we will give a simple branching algorithm for that problem. So, the branching, yeah, okay. So, Okay, let's try and prove this, right? Or should I assume the theorem and give the branching out? Okay, let me assume the theorem and give the branching algorithm, and then we will prove this. Again, proof is not very hard. I mean, proof will use this essentially, nothing much. Let me prove at least one direction of this because that's useful for my algorithm. So if suppose there exists an x in V such that opt of VCLP minus x is strictly less than minus half, right. So what am I saying? So here is my vertex x, here is the remaining graph, and I take this graph and solve my LP, and it turns out the LP value is strictly less than half. I mean, it dropped by more than half from whatever its original LP value was. But so what does it strictly less than means? Because the values are all 0, half, 1. I claim this means that this is simply less than or equal to opt of VCLPG minus 1, right, because every vertex gets a value 0, half or 1. So, okay. So, is this clear that if it's strictly less than this minus half means it can't be like this minus a 3/4 or something, because every value gets only half, half, half or 1 or 0, right. So, they are all actually multiples of half. So, and its objective function is the sum of the values. So, it will always be a multiple of half, everything will be a multiple of half the sum. So, it will be less than or equal to minus 1, right. So, now I will produce you a solution for the original LP which works like this. So, what do I do? What is the solution? So, I will set this to 1, I am going to set this value to 1 and set these guys to whatever that LP G minus x ka LP value is, right. I put this 1 and I claim that that will actually satisfy all the constraints of the original graph. Why? Because since I put this 1, it will cover all these edges, and within edges here they were anyway G minus x constraints. So, what is my total value now? It would be less than or equal to, but it cannot be less than optimum. So, it will be equal to. So, what I have shown? I have shown you a solution for the original LP which is not all halves, because this is 1. Okay, so, that shows one direction. If there is some x that violates this constraint, all halves is not the unique optimum solution. Okay, let me just go over it again for people who missed it. So, suppose there is a x such that this happens, then since the values are all 0, half, 1, strictly less than means that it is actually less than or equal to this. Now, let x v prime equal to, so let me just give, okay, so y x is equal to 1 and y v equal to whatever the solution for BCLPG minus X. Now, this is an opt solution for BCLPG, and that is not all halves. So, I will show the other direction later, but now let me just get to the algorithm. So, what am I going to do? I do this pre-processing, solve the LP, collect all the ones into my solution, throw away all the zeros, look at the remaining graph. In the remaining graph, I am going to try and remove one vertex at a time, solve the LP and see how much the LP value drops. If for any x the LP value drops less than or equal to this, then I have another handle to pre-process now, because I have another solution to the original LP which is not all half, then I can do this pre-processing again, right. So, I keep doing this pre-processing until for every x in V I have this situation, okay. Okay. So, now I am going to do my branching algorithm. So, what is the branching algorithm? I probably do not even need the converse, I think. It is enough. I mean, this is the property I am going to be using. Pick a non-isolated vertex and branch on it, okay. So, in one branch x is in solution, in the other branch I include all its neighbors into the solution, okay. So, x is not in the solution, this is my branching algorithm. Let us now see what happens to the measure. What is my measure now? K minus the LP opt, okay. If it is just K, clearly in both branches it drops, but that is not my measure, right. Okay, so now I get this new graph G prime. So, there is a K prime, there is an LP opt of G prime. Let us see what happens to both these quantities in both these cases, and then we will see the drops in each branch, that will tell us the height of this search tree, then we get the branching algorithm. Okay. Okay, so what happens to K prime here? Because my problem is to find a vertex cover of size K. The parameter happens to be not K, but something else. So, now I picked one vertex into my solution. So, now in the remaining graph I should look for a vertex cover of size K minus 1. So, K prime becomes K minus 1, right. Okay. What happens to the LP opt of G prime? If that also happens to be LP opt of G minus 1, then I am sunk, right. Then the difference does not drop, okay. But we know this, we are at this stage, we reached here when this happens, because otherwise we had a way of doing some pre-processing. So, we know that the LP opt of G prime is greater than or equal to LP opt of G minus half. Okay. So, now what is the difference? So, K prime minus LP opt of G prime is greater than or equal to, sorry, it is less than or equal to, because it is minus K minus LP opt minus, so it is minus 1 plus half, so it is minus half. Agreed? Right? My measure, see, when we did the vertex cover branching, K was my measure, and in each side this was K minus 1, K minus 1, and that gave us a recurrence relation of T of K equal to 2 times T of K minus 1, and that was a 2 power K. Okay. So, in particular I care about what is the value of the measure in each of these branches. So, here my measure is this difference K prime minus LP opt. Since LP opt is at least this much, it is at most K minus LP opt minus 1 plus half, which is minus half, which means the new measure, if I call this as some mu prime, is less than or equal to mu minus half. Which is good, because it actually drops. Okay. The problem is if it does not drop, because if it remained a K here, then I do not get a good recurrence rate. So, I need some drop. So, in this branch my measure drops because K prime drops by 1, but the LP does not drop by 1, it drops by at most half. So, the difference drops by at least half. Now, let us look at the other branch. Here I think I need the fact that all halves is the unique optimum solution. In the other branch, I need the converse. Okay, so let us see. So, what happens to K prime here? K minus degree of x, right, because that is the number of vertices I picked into my solution. Now, let us look at and I want to prove something like this, that LP opt of G prime is greater than or equal to LP opt of G minus d of x minus half. Or plus half. Yeah, if I, so this is something we will show. To show that, then I have something similar like this, that if I look at the difference, K prime minus LP opt would be less than or equal to K minus the degree of x minus LP plus this. So, K minus LP, this will cancel out, and I get, so I think I would say plus half. Yes, yes. So, that is what I was going to show. If I show this, then I can say in this branch also my mu prime is less than or equal to mu minus half. Okay, is that clear? So, this is what we will show, that K prime decreases by so much, but LP opt does not decrease by that much, it's at least this plus a half. So, that half is a saving grace to show that mu prime the measure decreases by at least this much. So, now okay, I have to prove this, I have to prove the converse of this, which I need to prove this. What is my running time now? What is the recurrence relation? So, recurrence relation would be like T of mu is less than or equal to 2 times T of mu minus half, where mu is this difference, right, K minus the LP opt. So, what is the solution to this recurrence? Four to the power mu, right, because just to one more level you will get 4 times T of mu minus 1. Okay, so, this is like a 4 power mu and I.e. K minus LP opt. Okay, so, that is what I wanted to show. So, the cleverness is in not just branching at any point, you do it after you reach all halves as the unique optimum solution. Then you branch at any vertex and branch, we can guarantee that the drop in the LP is not, it does not nullify the drop in the value of K prime. There is some half left. So, you have a good branching algorithm, you can bound the height of this by at most 2 mu. So, you get 4 power mu. So, the two things I need to show is the converse of this, that if this is not the case, then all halves is a unique optimum, and if all halves is the unique optimum, then this happens. Okay. Let us try and show this, that is easy. Then I am going to, then I will do some interesting corollaries of it for different problems, because it is. So, by the way, this 4 is not the best base, it has been improved. One can play around a little bit more by picking carefully chosen vertices. So, it is now it is 2.618 or even 2.23 or something is the base. Okay. 1.3 branch, I think. Okay. So, let us see why this is true. Okay. So, similar kind of an argument like what we did here, that suppose, so what is the story here? I have x here, its neighbors here, and this is the remaining graph, right. This is G prime, right. This G prime is this graph. I have deleted x and all its neighbors. So, this is removed. Now, I claim that the LP of this optimum value does not decrease by much. Suppose not, right. Is strictly less than again strictly less than means what? Less than or equal to what? Yeah, you can get rid of this because of this, right. It is strictly less than or equal to this. So, now guess what I would do? So, this is for G prime, right. So, I will take that LP opt G prime here, put all of these guys as 1, put this as 0. I will give you a, that gives you, I claim is a new solution for my original LP. Clearly, it is a solution for original LP because all constraints here are satisfied because of G prime. By putting all of this 1, I have satisfied edges across constraints. So, now what is its objective value? It is this plus this, which is equal to LP opt, and I have produced you an optimum solution for the original graph, which is not all halves, because I have a 0 here and all the ones here, which is a contradiction to the fact that we are sitting with all halves the unique optimum solution. Okay, so that this follows if I show this. Yeah. Okay. So actually, I mean, it's the same game we are playing. It's no big deal. Even the converse is very similar game. Okay. So I proved one direction. What did I say? If there exists a x in V, I said it's not the unique optimum solution. Suppose all halves is not the unique optimum solution. Okay. So this direction. If all halves is not the unique optimum solution but every value gets 0, half or 1, then there must be somebody which gets actually 1, right, because the optimum value is summation x v by 2, because all halves is a solution, because otherwise we would have done our pre-processing, ones and zeros are gone. Finally, all halves is an optimum solution, because we solved LP opt, gotten rid of ones and zeros, and what we have is halves, and all halves is an optimum solution for the problem. So if it is not the unique optimum solution, some other optimum solution will have some value less than 0, less than half, some value greater than half. But because of this Nemours theorem, the greater than half guy must be 1, right. Now take that vertex V which gets 1, look at the remaining graph and argue that for that this condition will be violated, right. I want to show that no, am I? So I showed that if there exists an optimum, then the all halves is not the unique optimum, and yeah, I am saying no, it's not this direction, it's the other direction. If this is true, I want to show that all halves is the unique optimum. Suppose not, pick some optimum which is not all half, it must set some variable to 1, remove that and look at the LP value of that and argue that that violates this constraint. Okay, so one important point which I really did not emphasize, which is important. So that's it, that's the end of the algorithm. Okay, let me just step back and tell you what I have done. We have done some pre-processing until we reach the situation where the unique optimum solution is all halves, and there I simply picked a non-isolated vertex and branched and argued that the drop not in k but in the difference k minus LP is at least half, resulting in a 4 power k minus LP opt algorithm for the problem. So the base, I mean, has become larger now. So the contrast is we had 1.28 power k, and here now I am saying it's 4 power k minus LP opt, right. The base has become larger, but it's compensated by the fact that at the exponent you have possibly much smaller value. And I also said even the base has been improved later, it's currently 2.3 or something, right. And the other key thing is that important thing about branching algorithms, you want to make sure whatever your measure is, which is a function of k, and it drops at every step. That's what helps us to bound this height of the tree. But it's also important that so there are some pre-processing we do, right, apart from branching. At the pre-processing step, it's also important that the measure does not increase. It doesn't have to drop, okay, because you're not dealing with any recursions and so on. But if it increases, then you have a problem, because you are applying a pre-processing step, some polynomial number of steps, and if every time your k keeps increasing, the game is over, because now k itself might have become you're looking for a vertex cover of size k plus n by 3 or something like that, and then you have a 2 power f of k algorithm means nothing because it's an n. So we did not do carefully, but that's also important that whenever you are doing some pre-processing rules, make sure that the k remains the same or decreases but does not increase. We did check when we are k was the parameter, in all our earlier branching algorithms or in bus kernelization, k always remained the same or it dropped. But in this cases, since the measure is k minus lp, you also have to check carefully that that difference doesn't increase. It remains the same or it drops. Okay. So I'm not going to do that, but that's another easy exercise based on all these nice LP properties. But I'm going to mention a couple of corollaries which are interesting. One is the problem we started off with, k minus matching, right? That is what I was interested in. So I have the input, my parameter is k minus size of this matching, and the question is the same. So this also has a how does this follow? So in the, if you draw a line, my maximum matching is somewhere here. Okay, the size of the maximum matching. Where does vertex cover lie? Above this, right? So this is the size of the minimum vertex cover in a general graph. In the bipartite graph, both are same. In general graph, it's above. Where does LP optimum lie? LP optimum is below this. We know that, right? Because more relaxation, minimization problem. So LP optimum is below this, but is it below this or above this? Above this. Okay, why? Yes. Hmm. Yes. Yeah, one line missing in between. I mean, you're there almost. So if you recall the LP, LP has for every edge xu plus xv is greater than or equal to 1, right? Suppose I write this for every edge in the matching, right? So I look at this constraint for every, I mean there are more constraints, but if I look at the variables for every edge in the matching, then that this sum is greater than or equal to 1, this is greater than or equal to 1. So, that means that this the sum of all these values must be greater than or equal to size of the matching, right, because these are all disjoint. And LP's objective function contains all these plus more. So, it will be at least size of the matching. I need to satisfy this constraint, does not matter whether you put 1/4 and 3/4 or whatever, this pair sum must be at least 1. This pair sum must be at least 1 by the LP optimum, LP feasible solution. So, if you sum all of this, the sum of these variables in any feasible solution must be at least the size of the matching, and the LP's objective function has sum of many more things. So, it is at least greater than or equal to maximum matching. Okay. So, now I was asking, is there a vertex cover of size? So, clearly the k has to be somewhere here, right, because this is a minimum vertex cover. So, k which you are looking for. So, so what I want to say is, right, good. So, what I am saying is, you are looking for a vertex cover of size k, and if you look at k's difference with LP, if I am giving this as a parameter, we had a 4 power mu algorithm, right. But if I give you this parameter, because of the scale is even more than this. So, that means I am giving you more time. So, all I am saying is k minus LP opt is less than or equal to k minus size of the matching from this picture, because the k I am looking for is somewhere in this range. This difference is less than or equal to this difference, because LP opt is greater than or equal to maximum matching, okay, as LP opt is greater than or equal to size of the matching. So, a 4 power k minus LP opt is less than or equal to 4 power k minus matching algorithm. So, the solution is run this algorithm, that is it. That itself is 4 power my new parameter, because basically my new parameter is larger than my old parameter. So, if you are giving me more time, so it is even better. In fact, there is a paper which is 2 years ago, which looked at, I mean this difference is smaller or this difference is smaller, and based on that there is a new parameterization, right. It is called raising the bar on vertex cover parameterization or something like that, and it gave an FPT algorithm with some new parameterization, which I forget, it is some I don't know whether anybody remembers, it is 2 times LP opt minus maximum matching or something like that, k minus this. But the point is that this is, I mean, what I want to say is, it is still very active area of work, right. You can, there are various ways of parameterization, and and things get interesting. Okay, I will just give you one more example, which another corollary of this, and then we will stop, and that is a very natural parameterization question. Which is the following: input is G, parameter is K. The question is, does there exist a subset of size at most k such that G minus S is bipartite. Okay, so vertex cover is asking for a subset whose removal makes it edgeless. Feedback vertex set is asking for a subset whose removal makes it a forest. This is asking for a subset whose removal makes it a bipartite graph. Okay, so this is called odd cycle transversal. Right. So S covers every odd cycle. Again, if you think about a simple FPT algorithm, not very obvious. If you want to do some branching, you want to find a short odd cycle and then do some branching. But why should there be such a short odd cycle? Right? It was hard enough even for feedback vertex set to need not be short cycle, minimum degree 3. There are various things we did for feedback vertex set. You can't easily do all that. But turns out there is a very nice reduction from here to here, which we can use and get a simple 4 power k algorithm. Okay. So, how does it work? So, you are given this graph G where I am interested in odd cycle transversal. So, what we will do is given G, we will construct this G prime, which has 2 copies of G with the corresponding vertices joined by an edge. Okay. So, now the claim is G has, so let us call this as OCT, right, odd cycle transversal, OCT of size k if and only if G prime has a vertex cover of size n plus k. Okay, very simple exercise. Prove it, we will look at it tomorrow. But suppose I prove this. Now, so this problem, is there a OCT of size at most k, boils down to, is there a vertex cover of size at most n plus k here, right. So, now I apply this algorithm, but what is the matching size here? N, this is a perfect matching, there are only 2 n vertices, n matching size n. So, I have an algorithm whose running time is 4 power whatever I am interested in. What is the solution size I am interested in? No, for the vertex cover n plus k. So, n plus k, so I have a 4 power k algorithm to test whether this graph has a vertex cover of size n plus k, which means I have a 4 power k algorithm to test whether there is an OCT of size k. right. But it's important, the parameter here is not the solution size. It's k minus the matching size. That's what helped me kill this n. Okay. So if I mean, we know for vertex cover there was 2 power k kind of thing. That would only give me 2 power n plus k. But I can subtract out the matching size, and here there is a matching of size n. So I have a 4 power k algorithm to test whether there is an odd cycle transversal of size at most k in the original graph. Remember, we still do not have such a nice C power k algorithm for feedback vertex set. For feedback vertex set, whatever we have seen is only like k power k. There is no nice C power k, but here it's like one shot simple reduction. But this is a very simple exercise, prove it. And we'll see more corollaries and proof of this and things tomorrow. Yeah.